Okay, so we're going to talk about Fourier transforms today. These are analogous to Fourier series, but they are a limit of what that Fourier series becomes as you let the width of the interval of the function that you're considering go to infinity. Okay, so we saw for Fourier series that we could take any function between minus L over 2 and L over 2, this fundamental interval, and that function might look something like this. It might not even be periodic, but we can take a periodic extension of that, periodic images of those to the left and to the right, as many copies as we want, each of width L, and build a Fourier series. And remember that the Fourier series was written this way. We had a leading coefficient that looks like a cosine of a zero frequency term, and we had a whole bunch of finite frequency terms that are cosine and sines, right? So this is 2 pi kx over L in the argument of each of these, and that makes the interval of width L. Okay, so we of course need the sines to describe odd functions, and we need the cosines to describe even functions. And for any function f that is a mixture of both even and odd parts, we can isolate the odd parts of that function by doing an anti-symmetrization, that is f of x minus f of minus x is always an odd function, and you know, if we divide that by half, then that will turn out to isolate those sine components of the Fourier series. And we can do the same thing with the even functions. We symmetrize our function f, that is, we add f of x and f of minus x, divide by 2, and that gives something that should be equivalent to all of the even terms of the Fourier series. And of course we can reconstitute our whole function f by adding the odd and even parts. You can see that from these two expressions. You can also see that from adding the sines and the cosine even parts of the series representation, and of course you get back the f of x there as well. Okay, so you know, this is the common way that we write Fourier series, is in terms of sines and cosines. But it's just as well we could have started by thinking about e to the functions of the type e to the purely imaginary argument, e to the 2 pi I k x over L, and those now are going to be cosine plus I sine of all of this stuff, 2 pi k x over L, which is a periodic function. It's purely imaginary. If I consider e to the I k x over L and e to the minus I k x over L, then the real parts will vanish because they have even symmetry, and the odd parts will not necessarily vanish. And so we can choose the f sub k's then to match any function that way as well, by starting with these kinds of functions. Okay, so now my sum has to go from minus infinity to infinity to include the ik and the minus ik, is the basic idea behind this way of representing a Fourier series. Okay, so these things also have a orthogonality property. Of course, they really are cosines and sines, but you can derive the orthogonality relations and then take the inner product with one function to isolate what that expansion coefficient is. So this is the expansion coefficient in the Fourier series, and so if you have used this orthogonality, then you can isolate this expansion coefficient with this formula. Okay, so now what we're going to do is go over to this other page and look at what happens when we take the limit as the length of the interval goes to infinity, and in that limit you find that you can write down this generalization of the Fourier series for an infinite interval in this form. So now I have a continuous set of frequencies, and you can imagine why it would be continuous, because for any finite frequency, if I have an infinite domain, that of course is some fraction of as you go out farther and farther, larger and larger numbers, of course you can represent anything finite as a fraction of that larger number. You know, as you go larger and larger, the intervals that you get become finer and finer. Okay, so this is basically what's happening here. This is the Fourier components of the oscillation with wavelength 2 pi over L is equal to k. Okay, and so this e to the ikx, now we integrate out all wavelengths with all of their components weighted, and it gives us back the original function. Okay, so this is like the eigenfunction expansion that we did earlier, but now we are doing an integral over a continuous range of indices, which are wavelengths in our, frequencies in our problem, and the components of each eigenfunction, if you want to think of them that way. We're expanding in these e to the ikx functions. So those are our eigenfunctions, and there's a whole continuous spectrum of them. And to isolate the components, I have to take the original function in an inner product with the complex conjugate of that basis function, e to the minus ikx now, and integrate, do the inner product over x. And this is basically what's happening in this formula, right? So you have the Fourier coefficients here and the eigenfunction expansion in terms of this continuous basis, and that's a Fourier transform. So these things have a number of useful properties. Most useful among them is that it's a one-to-one mapping, right? So I should note that they don't work for all functions. There are lots of functions that don't have Fourier transforms. For example, the simplest one that comes to mind is the function 1 doesn't have a Fourier transform, right? So anything that for which this oscillating kernel doesn't converge is not going to give, this integral over this oscillating kernel multiplied by the function doesn't converge, is obviously going to give you a problem. But they do have a lot of useful properties. This one-to-one correspondence with the function that you Fourier transform and the function that you get back when you do the inverse Fourier transform, of course, is why we can properly call it an inverse. And that's what makes them extremely useful. And of course, you may remember from differential equations that they convert derivatives into powers of omega, or powers of k. So we'll see that property in a little bit. But let's do a little very, very simple example and take the Fourier transform of the delta function. Okay, so here is by definition what we're doing when we take the Fourier transform. There's the function, the delta of x minus x naught, and we have e to the minus ikx. We're going to integrate out all values of x from minus infinity to infinity. And of course, the only one that's going to contribute is x naught, because it's a delta function. And so we get 1 over square root of 2 pi e to the minus ikx naught. Okay, so this is the Fourier transform of a delta function centered at x naught. What if we now ask, what's the inverse Fourier transform of this function? Well, it should be the delta function. And by definition, that inverse Fourier transform is this thing, right? So we can do that integral. So this is the formula for the inverse Fourier transform. We take the f of k, which now is this thing with a parameter x naught, multiply by e to the ikx, integrate out all values of k. Okay, and that of course can just be written more compactly in this form, and so we discover really an identity here for the delta function, and that's called that has a name. It's called the Fourier representation of the delta, and it's 1 over 2 pi with this integral from minus infinity to infinity, e to the ik x minus x naught dk. And of course, if x is equal to x naught, this becomes a integral of 1 from minus infinity to infinity, and obviously diverges at that one very special place for any non-zero value of, or non-x0 value of x. This is just giving us contributions that cancel and has no real value. Okay, so let's say a little bit about its behavior under differentiation. So if you consider a function f of x, which has a Fourier transform f hat of k, then the derivative of f of x has a Fourier transform that is ik f hat of k. Okay, so it's a remarkable property, really. I mean, remarkably simple to derive as well, but it is indeed remarkable that this integral transform takes the derivative of a function and relates its transform to the transform of the original function by just multiplying it by this factor ik. And we can do this recursively. We can go on down now and keep using this formula. F prime prime of x gets mapped to minus k squared f hat of k, and higher powers of k every time you get a new factor of ik out in front. And so we can use this to solve differential equations. It's quite a common exercise, this little Cauchy problem. And so you can do this by doing a Fourier transform. We're going to take, well, this is the problem. It's the diffusion equation. For all values of x and for all time greater than 0, we're given an initial condition, u of x0 is phi of x. Okay, so we cannot make this problem dimensionless. We cannot find any obvious length scale. We can't do an eigenfunction expansion, even though it's a problem that's perfectly homogeneous. But you know, there are some problems here with solving this, except that the Fourier transform can do it just fine. We're going to transform x into k, which is going to leave us with a function of t and k. Okay, we call that function u hat. So u hat of t is the derivative with respect to t of u hat should be, after Fourier transformation, equal to minus k squared d times u hat. Okay, so now we can actually solve this thing. This is really a trivial ODE. It's just an exponential decay. So we get u hat of k at time 0 is multiplied by e to the minus k squared dt. And if this thing on the left side is the Fourier transform of the solution, then when I plug in t equals 0, I must find that you know, this thing at the initial time goes to the Fourier transform of the initial condition at the initial time. Okay, so I basically already inserted that as a property of the problem, but of course that is going to end up being phi hat of k, and so we know that u hat of 0 is phi hat of k, and u hat of kt therefore is phi hat times e to the minus k squared dt. Now, inverting Fourier transforms is usually not so incredibly difficult. But you know, you don't want to just rush into the integration. In this case, there is a very useful result, the Fourier convolution formula. When you see a Fourier transform that is a product of two Fourier transforms that you recognize, you don't have to plug this function of k into the Fourier inversion integral and crank through. You can actually use something called the convolution integral. Okay, so the Fourier convolution is this character that we will discuss now. So this is the definition of a convolution of two functions. It's f convoluted with g is defined as an integral over f of x minus z times g minus z times g of z, and we're integrating out this dummy variable z, which leaves behind a function of x. Okay, and that's that convolution. Okay, so what is the Fourier transform of one of these convolutions? Well, there are a number of steps involved in this derivation, but they're all pretty elementary. So the first thing you do is just write down the definition, and that definition is here. So I've got f of x minus z, g of z, 1 over square root of 2 pi. That whole thing is the function that I'm Fourier transforming. It's a function of x. And now what we will do is to switch the order of integration and pull everything that only depends on z out to the left. Okay, so now we have these leading things that only depend on z. And on the inside now, we have an integral over x, e to the minus ikx f of x minus z. Now this is an integral from minus infinity to infinity. We can start from anywhere we like and recenter this thing. Therefore, and so we're going to recenter it in such a way that y is the difference between x and z. And now this becomes f of y. The integration bounds are still minus infinity to infinity. We didn't change anything there because what's changing is x and y, and they both have to go to the same place, minus infinity to infinity. E to the minus ik y comes from rewriting x in terms of y plus z. That kicks out an e to the minus ikz term here, which now just becomes part of the integral over z. And what happens now is that one Fourier transform is the Fourier transform of f, and the other one is the Fourier transform of g. And so you get the product of g hat and f hat from the Fourier transform of the convolution of f and g. So f and g, when they're convoluted, map through Fourier transformation to the Fourier transform of the separate functions g and f. All right, so this is a quite useful formula, and it useful in both directions, of course. Fourier transforms always have this inversion one-to-one characteristic. So now we can return to our PDE and recognize that the inverse Fourier transform of the product of phi hat with e to the minus k squared dt is nothing more than the inverse Fourier transforms of the two separate pieces convoluted with each other. Okay? So I think that is apparently it. Okay, so I think I'm up, and we're going to finish this problem that abruptly ended last time, and so what we had was a problem where we had a Fourier transformed solution of a problem that was phi hat of k multiplied by e to the minus k squared dt, and we showed that the solution after Fourier transformation back would just be a convolution of the two functions that had been Fourier transformed to give us these things. Okay, so one of those is phi of x, right? That one is super easy. Now the question is, what function gives us a Fourier transform of e to the minus k squared dt? So that one we can invert. It's 1 over the square root of 2 pi integral from minus infinity to infinity dk. This is the definition of the Fourier inverse. So e to the ikx multiplied by e to the minus k squared dt. We're integrating out all k's, so this is going to end up being a function of the x. The exercise you have to do here is really nothing more than completing the square and the exponential, and then doing the Gaussian integral. Okay, so there are some messy steps here. Tables can help a tremendous amount. Mathematica can help a tremendous amount. So we end up with e to the ikx minus k squared over 4a if I let a squared be equal to 1 over 4 dt. Okay, why change nomenclature like this in the middle of the problem? Well, because the table that I have is in terms of a constant a squared in the denominator, and so that we can only get that if we make the a squared be equal to the 4 dt, the thing that we really have in the denominator. All right, so that's basically the strategy. Redefine everything in terms of stuff that you have in your table, or plug it into Mathematica sometimes, and it can just give you the answer. That's quite nice. But what you have at the end of the day is that the inverse Fourier transform of e to the minus k squared dt comes out to be a normalized one-dimensional Gaussian. That is 1 over square root of 2 dt times the exponential of minus x squared over 4 dt. Okay, so this thing now is what we can use. So now we have these two functions of x, right? So we have this one, and the inverse Fourier transform of phi hat multiplied by e to the minus k squared is a convolution with this and this. Okay, so we take our Fourier convolution integral, and we write that down. So now u of x and t is going to be the solution to our problem, and it's 1 over the square root of 2 pi times an integral of 1 over the square root of 2 dt e to the minus x naught squared over 4 dt times phi of x naught. Okay, so now we're integrating out the x naught, ending up with a function of x. Now what is customary is to take everything on the outside here that's a constant, lump it in with this piece of the solution, this part that depends on x minus x naught and the 1 over square root of 2 pi, or 2 dt. It's going to end up being a 4 pi dt after lumping together with this term. So what's typically done is that we call this whole thing, apart from phi of x0, a time-dependent Green's function, right? So this guy is telling you, if I had started with a delta function initial condition with everything centered at location x naught at time 0, what would be the solution after times t in terms of a g of x given location x0 at the initial time? Okay, so what you're doing now is you're adding up contributions of really an infinity of those, all very, very small weight, right? So the amount of stuff located at x0 is phi of x0 times that little tiny interval around x0 that you're integrating, and each of them are spreading out in time according to this Green's function. And this now is a time-dependent Green's function, where time is this parameter marching forward, making everything blur out over time in the solution. So that's our Green's function, and we now know how to find Green's functions in principle for time-dependent problems, which are quite useful things in some fields. So let's see, just for these closing moments, how to deal with symmetry and solve problems that are only defined on the half domain. Our Fourier transformation is over everything from minus infinity to infinity, but quite often we can create an image problem and solve that image problem, and if the image problem is created appropriately, then it will also satisfy the boundary conditions for the semi-infinite domain problem. Okay, so here's one of those where we're going to consider x greater than 0. We have a diffusion equation. We have an initial condition that says that this is an exponential decay from 0 out to infinity. And we have a boundary condition that is a no-flux boundary condition at the origin. Okay? So how do we automatically satisfy that no-flux boundary condition at the origin? What we do is we just extend the initial condition to negative infinity and solve the same partial differential equation. And what you have now is an infinite domain, not a semi-infinite domain. And it has this initial condition, e to the minus absolute value of x over lambda. Okay, so now our answer, we can immediately write it down because we have already solved this problem on the page over here. This is what we found when we were doing all of this stuff, is that our answer is just going to be a convolution with that time-dependent Green's function multiplied by that initial condition. And it will automatically satisfy those boundary conditions because the Green's function itself satisfies those. Okay, so this is a little picture of what the solution looks like. This red curve is the initial condition. Everything to the left of 0 is sort of fictitious. We just used it as a device to satisfy our boundary condition and to make it possible to do this problem by Fourier transformation. What's happening as time goes on is that this thing is flattening out, and getting wider and wider. The total area under these curves is being conserved. There are no sources and sinks in the original equation, and so this is the solution. And it's pretty easy and painless to get that by Fourier transformation. Let's see the rest of this problem. We can also do these symmetric extensions to solve problems like this. Okay, so here you have an initial condition, the same exact one as before, in the same formula even as we had before. But now we have a Dirichlet boundary condition that says that u of 0 and t is equal to a specific value. Okay, so now in order to make that 0, we can just do an odd extension of our function. So we start out on the right with e to the minus x over lambda, and on the left with minus e to the minus e to the x over lambda, not e to the minus x over lambda over here. Okay, so now we know that this is going to have an answer that is just a convolution of our initial condition extended to the full real line, multiplied by this time-dependent Green's function, and doing that gives a solution that now decays pretty quickly, right? So notice that the one up here was very, very slow, gradual decay. The one over here has exactly the same. It has exactly the same. Well, I forgot what I was going to say about that. It has exactly the same initial condition, but it's decaying much, much faster because the area under this one is not conserved, right? The right side is gradually annihilating the left side, and eventually this will just go to 0, this whole solution. Okay, that's it. Let's see if I can merge those videos.